This video is on monotonic and bounded sequences. Alright, we start with a result from analysis. It's called the monotonic sequence theorem. It says that if a sequence is bounded and monotonic, then it converges. Alright, we'll talk about what each of those means first. So we're going to go through and define what monotonic means, and then how to show that a sequence is monotonic. We'll define what bounded is and show some techniques for showing that a sequence is bounded. And then if you're able to show both of those things, then we know that the sequence converges. We don't necessarily know its limit, but we do know that it converges to something. Okay, let's start with some definitions. A sequence is monotonic if it is either always increasing or always decreasing. Increasing is a pretty intuitive definition. A sequence AN is increasing if AN plus 1 is greater than AN for all n. And a sequence AN is decreasing if AN plus 1 is less than AN for all n, just meaning the next term is smaller than the one before it. In a lot of proofs, we'll only be concerned with large n, so we may make a proof that a sequence is monotonic for large n, just meaning that it's increasing for once n is large enough, or it's decreasing once n is large enough. That's sufficient for the proof of the monotonic sequence theorem above. If the first few terms are alternating, or if the first few terms are increasing, but then eventually it's decreasing, so if a sequence is going up at first and then eventually is always decreasing, for large n would just mean like from here on, then it's decreasing. That's not technically with the definitions, but that'll be enough for our proofs. So the next thing we're going to do is look at how to prove that a sequence is monotonic. So let's look at 3 methods for showing that a sequence is monotonic. So to show that it's monotonic, which means that we're trying to show whether it's increasing or decreasing. Let's spell that right. Then if it's easy enough, it might be possible to just look at the formula for a sub n plus 1 versus a sub n. If it's clear that one is bigger than the other, then we should use that. If it's not clear, then we should go to something more advanced. The second thing would be that we could convert to a function f of x. So we've talked about before, a sequence is not continuous, but f of x typically would be continuous. And then we would look at its derivative. If we can prove that the derivative is always positive, the sequence would be increasing. If we can prove that the derivative is always negative, the sequence would be decreasing. And then the third option is to look at the ratio a sub n plus 1 divided by a sub n. If we can prove whether that's larger or smaller than 1, and we know all the signs are the same, then that can indicate whether a sequence is increasing or decreasing. Before doing any of these things, we should think first. So if you have a sequence that is alternating, where it's alternating positive, negative forever, there's no way that's monotonic, because clearly it's bouncing up and down and it's not always going up or always going down. Okay, so let's look at some examples. So we're going to say show that the sequence is monotonic, or explain why it's not. Alright, and so the first problem I want to look at is a sub n is equal to 1 over n. And so this is a pretty straightforward sequence. When there's something this simple, then it's worth just looking at a sub n plus 1. A sub n plus 1 means that we replace n with n plus 1, so we get 1 over n plus 1. It's easy to compare that to 1 over n. So we know there that the numerators of the fractions are the same. We know that the denominator of 1 over n plus 1 is larger than the denominator of 1 over n. And so because the bottom is bigger and the top is the same, the fraction on the left is smaller than the fraction on the right. That's true for positive fractions. If you think about things like 1/3 versus 1/4. 1/4 is smaller than 1/3, even though maybe that's counterintuitive at first. We know that if you divide a whole into 4 parts, that's smaller than if you divide it into 3 parts. And so 1/4 is smaller than 1/3. When you talk about negatives, that's reversed. But here we know that everything is positive, and so that's not an issue on this problem. So this is one where it's simple enough to just compare the two formulas. We know from what we've written there that an plus 1 is less than an. So then an is decreasing. And so that's a proof that it's monotonic. Because we know that it's decreasing. Monotonic means it's either increasing or decreasing. Let's look at a second example. Okay, so if we have an equals -1 to the n over 2n. So you can start looking at an plus 1 versus an, but the -1 to the n there almost always would indicate that a sequence is alternating. That's the case here. So if it's -1 to the n, when we plug in even numbers for n, -1 to the n is +1. When we plug in odd numbers for n, -1 to the n is -1. The bottom on this for all large n is going to be positive. And so this is alternating positive, negative, which means it's not monotonic. So it's not always increasing and it's not always decreasing. And our explanation as to why is that it's alternating. Okay, let's look at a third problem. So if we have an equals, say, 4 over 2n plus 3, then again, this is a relatively simple example, and so what we're going to look at is just an plus 1 versus an. So an plus 1 means that we're going to replace n with n plus 1, so it's 2 times n plus 1 plus 3. That gets us 4 over 2n plus 5 with the algebra there, so you distribute the 2, you get 2n plus 2 plus 3, and then if you combine like terms, you get 2n plus 5. If we compare that to 4 over 2n plus 3, the numerators of the fractions are the same, and the denominator of the fraction on the left is larger than the denominator of the fraction on the right, which means that the fraction on the left is smaller. So again, an is decreasing, which means it's monotonic. So to finish our proof or our explanation, we just say, so then it's decreasing, which means it's monotonic. Okay, let's go to a more complex example. So let's say I have n over n squared plus 3. So here, if you start looking at an plus 1, it's not quite as clear which one is larger than the other. So if I were to do this, which is not what I'd recommend that we do, if I do this, I get n plus 1 over n plus 1 squared plus 3, which is n plus 1 over n squared plus 2n plus 4. To compare that to an, it's not as obvious here because even though the denominator of the fraction on the left is larger than the denominator of the fraction on the right, the numerator is larger on the left than it is on the right. So the numerator would indicate the fraction on the left would be larger, the denominator would indicate the fraction on the left is smaller, so it's not clear cut. We might be able to do some more analysis to figure out which one's larger, but it's an easier or more clean proof to go about this a different way. So rather than doing that, we're going to look at two different options for this. So the second option that we listed above, so we said there were 3 main ways to do this. So we can look at an plus 1 versus an. That's what we did on examples 1, 2, and 3. What we're going to do now is the second method. So we're going to convert to f of x, and we're going to look at the derivative. So here, what we're going to do is we're going to say let f of x equal x over x squared plus 3. We're going to look at the derivative of that. So the derivative of this is using the quotient rule. So we take the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. We simplify that, so we get x squared plus 3 minus 2x squared. And I'm going to go ahead and leave the bottom in its factored form. When we do that, we simplify that to negative x squared plus 3 over x squared plus 3 squared. Now we analyze that and figure out whether we can tell whether that is positive or negative, or do we not know. And if we look at the bottom, because the entire thing is squared, the bottom must be positive. So x squared is at least 0. When we add 3, that's at least 3. And when we square that, then obviously that's a positive number still. The top, negative x squared, is going to happen first, and then we're going to add 3. Negative x squared is going to be larger than 3 as long as x is at least square root of 3, but x is at least 2, then this would be the case. And so for large values of x, this is going to be less than 0. So we're just going to say for large x, in particular here, it's x greater than the square root of 3, or for integers, it's x greater than 2, greater than or equals to. That would make the top negative. So you have a negative divided by a positive, which means it's negative. If we remember from Calc 1, a negative derivative means that the derivative is, or that the slope is negative, which means the function is decreasing. Since f of n is equal to an for all n, then an is decreasing for large n. And so then again, it's monotonic. So this is decreasing, and that's a proof then that it is monotonic. Let's look at another example like that. All right, so if I have n squared plus 5 over 3n, again, if we just compare an plus 1 versus an, this is a little more complicated, so it may not be clear which one's larger. So we're going to try taking the derivative. In order to do that, we need a continuous function. So we're going to say let f of x equal x squared plus 5 over 3x. Then if that's the case, the derivative is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. That simplifies to 6x squared minus 3x squared minus 15 over 9x squared. That gets us 3x squared minus 15 over 9x squared. If we look at that, the bottom is positive for sure because we have positive 9 times x squared. X squared is at least 0, so it's positive. The top is going to be positive once 3x squared gets larger than 15. So we know this is greater than 0, and we're going to say again for large x, meaning large enough so that we're correct. We don't want to figure out exactly when that's true, especially if these get more complicated. Here it would be true when x is larger than the square root of 5. We can quickly solve the top in order to determine that, but for large x that's true. So this means f of x is decreasing, and then f of x is increasing. Since f of n is equal to an then, for all an is increasing for large n. If we want to get technical with the definitions above, so we could say that at the beginning it's not increasing, and we could list some values in order to determine that. That means it's not monotonic for all n, but it is monotonic for large n, and so we're going to stick with that in these videos. Depending on what your instructor wants, then that may not be the case in your class. But for our purposes, we're going to say for large n is good enough to prove that it's increasing. Okay, I want to do the same problem we did a few minutes ago, or just before. So x squared plus n squared plus 5 over 3n. So let's look at that problem again, but let's look at another method for that. So if I have n squared plus 5 over 3n, we can take the derivative, convert to f of x, take the derivative, and prove that it's positive. Another option is to look at the ratio an plus 1 divided by an. This is important for some things we're going to do later, and there's a few examples of this, like involving factorials, where you're not able to convert to a continuous function in an easy way. And so what we want to do here is we want to look at a sub n plus 1. So a sub n plus 1 is n plus 1 squared plus 5 over 3 times n plus 1, and divide by an. And normally we'll probably skip through this first step, but go ahead and write it for now as division. And then what that means is we're going to multiply by the reciprocal of the bottom. So we're going to flip the bottom and multiply. So we get n plus 1 squared plus 5 over 3 times n plus 1 times 3n over n squared plus 5. Now we're going to work out the algebra. And so if I expand n plus 1 squared, I get n squared plus 2n plus 1. But then I'm going to go ahead and combine the 5, so it's n squared plus 2n plus 6. On the bottom, I've got 3n plus 3, and then 3n over n squared plus 5. Now we're going to work out the algebra by distributing the numerators. So we get 3n to the third plus 6n squared plus 18n. And then we're going to distribute the bottom, and I'm going to put the terms in order. So 3n times n squared is 3n to the third. 3 times n squared is 3n squared. 3n times 5 is 15n, and 3 times 5 is 15, and so this is what we get. If you multiply in a different order, you'd want to rearrange it this way. So now, again, thinking about large n, if you look at the numerator versus the denominator, then we know that 3n to the third and 3n to the third are the dominant terms. That means that in the long run, the top is basically the bottom, or basically the same as the bottom, which means the limit of this would be 1, but on the top, we then add 6n squared, and on the bottom, we only add 3n squared. So the top for large n is larger than the bottom, which means that this fraction is greater than 1. We know it's positive because of the largest terms, but because of the second largest terms, we know the top is bigger than the bottom, which means this is a fraction like 10 over 7 or 40 over 39, and so this is something larger than 1. What that indicates is that an plus 1 divided by an is greater than 1. So if you follow through the whole sequence of steps in here, we're showing that this part is bigger than 1. When you have an inequality, you can then multiply by the denominator as long as we know the sign of the denominator. And so if we have an plus 1 over an is greater than 1, I'm going to multiply both sides by an. You have to be a little bit careful because when you multiply inequalities by stuff, if you multiply by a positive, the inequality stays the same. If you multiply by a negative, the inequality reverses. If we go back and look at the original formula, n squared plus 5 over 3n, we know that that's positive for a large n. So that means that when we multiply by n, and we're multiplying by a positive number, which does not reverse the inequality sign, so then an is increasing for large n. On this example, this is probably harder than using the derivative. We're going to look at an example where it would be very difficult, if not impossible, to use the derivative next. This is another technique that we're going to want to get used to because of something later called a ratio test as well. So here we've proven again that it's increasing. And so if you go back and compare the proof on 5 versus 6, it's the same problem, but two different methods. All right, let's look at another example involving a factorial. All right, so if an is n squared over the quantity 3n factorial. So here, two things to notice. One is the first method of just comparing the formulas for an plus 1 and an would be very difficult to determine which is bigger. The second method, converting to f of x, because of the way we define factorials so far, there's no way to define the factorial right now when we talk about integer values of n. So we can't really, or non-integer values of n, so we can't really do f of x equals x squared over 3x factorial. So what we're going to do is we're going to look at a sub n plus 1 divided by a sub n, and rather than writing it as a big fraction this time, I'm going to go ahead and write it as a sub n plus 1. So that's n plus 1 squared over 3 times n plus 1 factorial. And then instead of divided by an, we're going to go ahead and multiply by the reciprocal of an. So times 3n factorial over n squared. So now we're going to distribute the stuff on top, or in the first fraction. And so we get n plus 1 squared is n squared plus 2n plus 1. And then on the bottom we get 3n plus 3 factorial. And then there's nothing really we can do to simplify the right-hand fraction. But now we can cancel the factorials. And if this is something we're not familiar with, maybe go watch the video on factorials. It reviews a lot of that algebra, or maybe teaches it for the first time if you've never studied factorials before. But 3n plus 3 factorial can be rewritten as 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n factorial. We do that so now the 3n factorials will cancel. And so we get n squared plus 2n plus 1 over 3n plus 3, 3n plus 2, 3n plus 1, and then n squared. So if we look at the top now versus the bottom, if we were to multiply the bottom out, we would end up with the largest term being 27n to the 5th power. That's, for large n, 27n to the 5th power is much larger than n squared plus 2n plus 1. And so we can make the argument that this is less than 1 for large n. If you want to multiply the entire bottom out, that would actually be more formal, and we could do that because of time. I'm not going to do that here. That then indicates that an plus 1 divided by an is less than 1. And now we can multiply both sides of the inequality by an. That gets us an plus 1 on the left and an on the right. We don't flip the inequality sign because an is positive, and we can look back at the original formula to know that an is positive. Both n squared and 3n factorial are positive for all n. And so then this means that an is decreasing, which then means in turn monotonic for large n. Okay, let's talk about bounded sequences now. So we say that a sequence is bounded if it is both bounded above and bounded below. Let's define bounded above first. All right, so a sequence an is bounded above if there is some number m such that an is less than or equal to m for all. And we usually say n greater than or equal to 1, but a lot of times we'll say for large n again, or wherever the sequence is starting. But for the definition, let's go ahead and say for all n greater than or equal to 1. So what this means is all of the terms are smaller than m or equal to m. All the terms in the sequence are smaller than m. A sequence is bounded below, so same definition. If there's a number m such that all the terms are bigger than that. Man, greater than or equal to 1 still. All right, and so graphically, if we have a sequence, maybe it's alternating, so it's doing something like this. It doesn't have to converge, but let's say this one is converging to 0, but it's alternating. So, okay, so it's bounded above by a number like this. And so if it's bounded above by m, then all the terms are less than m, including the negatives. Let's say it's bounded below by n, and so it's bounded below by n because all the terms are bigger than that. M and n don't need to be positive and negative in general. They would have to be in this example, but it's bounded above by m, it's bounded below by n. 2 comments. One is that means the sequence itself is bounded. It's bounded above and below, so the sequence that I've drawn there is bounded itself because it's bounded both directions, above and below. Another thing is that if it's bounded by m, it would also be bounded by anything above that. So if this is some other letter p or some other number p, then if it's bounded above by m, it's also bounded above by p. There's not a unique bound above it. There's not a unique upper bound. There's not a unique lower bound. And if it's bounded by n, here it would also be bounded by q. If this a number q is down here, it's bounded below by q as well. So that means that this is less exact than some other things that we would like to do. When we try to show a sequence is bounded, we're just trying to show that it's bounded above by something and that it's bounded below by something. If it's bounded above by 2, it's also bounded above by 3, and it's also bounded above by 100. If it's bounded above by 2, though, it's not necessarily bounded above by 1. It could be, but we don't know that. Similarly, if it's bounded below, like if it's bounded below and this is say -3, it's also bounded below by -4 automatically, but maybe not -2. Maybe it just depends on exactly where that number is. And so let's look at a couple examples where we try to prove that a sequence is bounded. There's not as exact of a way to do this, but we can look at an example where we would show that something is bounded here. Okay, let's look at this example. So we're going to show that the sequence is bounded. an equals 6n squared minus 7 over 2n squared plus 6. Now what we're going to do looks really weird, and it doesn't necessarily apply to every problem. Like I said, this isn't an exact proof method. It's something we try to do that might work in certain circumstances. So in this case, we can look at the absolute value of an first of all. So let's say the absolute value of an is 6n squared minus 7 over 2n squared plus 6. The reason we're going to do that is because if we can prove in general that like the absolute value of x is less than, let's say, 15, then we know that x is between -15 and +15. And so the number 15, I'm just making up, it has nothing to do with this particular example, but if we're able to prove that the absolute value of something is less than 15, then we know it's bounded above, or it's less than 15 above, and it's greater than -15 below. So if we're able to prove that the absolute value here is less than something, we know it's bounded above by that, and it's bounded below by its negative, which means that it's bounded in both directions, so the sequence itself is bounded. So the technique here is that we're going to try to show that this is less, the absolute value is less than some number. And so the first thing I can see on this problem is that this would be less than 6n squared over 2n squared plus 6, because the only change I've made to go from the first fraction to the second fraction is I've made the numerator larger. So if we're talking about positive fractions, which is what we are here, if the denominator is the same and the numerator gets larger, the fraction gets bigger. Same idea, if I keep the numerator the same and make the denominator smaller, the fraction continues to get bigger. So I can say, okay, well then this is less than 6n squared over 2n squared. If that's the case, that's then 3. And so for large n, as long as the absolute value is what we said it was, which it is for large n, then we can say that the absolute value is less than 3. For more details on the absolute value, you should watch the absolute value video. That's in the prerequisite material part of the channel. But if you look at 6n squared minus 7, that happens to be negative when n is 1, but once n is bigger than that, once n is at least 2, then everything here is positive. The for large n is what we're going to use to kind of take care of that. What that means is the absolute value of an is less than 3. That means that an is bounded above by 3, bounded below by negative 3 for large n, and so then we'll say that an is bounded by 3. Again, this is not a unique answer. If it's bounded above by 3, it's also bounded above by 7 and 8 and 9 and anything else above 3. If it's bounded below by negative 3, it's also bounded below by negative 4. Do another example. So if we have an equals sine n over n. All right, so we're going to again look at the absolute value of this to try to prove that it's bounded above and below. So the absolute value of sine n, we can't really simplify. We need to keep that as absolute value of sine n, but the absolute value of n is n. And again, if we need to review absolute value, there's a video on that under the prerequisite material part of the channel. All right, so here we know that absolute value of sine n is always less than 1. Technically we know it's less than or equal to 1 if that makes it seem a little bit easier, but sine of an integer would never actually be 1, so we would be safe there to say less than. Less than or equal is good enough based on the definition we used for bounded before. So this is less than 1 over n. And now if we think about n for sequences, n is approaching infinity, so we're talking about n is 1, 2, 3, 4, 5, and so on. That means this is going to be less than or equal to 1. And we know that because 1 over 1 is obviously 1, 1 over 2 is smaller than that, 1 over 3 is smaller than that, and so on. So all of the fractions except the very first one are less than 1, and 1 over 1 is 1. And so we've now proven that this is bounded by 1. So then an is bounded by 1, but we're just trying to prove at this point that it is bounded. Like I said, the proofs for bounded are a little bit weirder than most. There are more advanced techniques that we could use in later courses. We just need to be able to think about what bounded means and then maybe deal with some true-false type questions that we'll talk about in another video and on some practice. All right, I think that's it for the bounded and monotonic video. If you have any questions, feel free to contact me. Thanks.